Now for almost all the atoms on our periodic table, we're going to have our standard filling rules apply, but we do have a few exceptions. You could approach those purely in a memorization form, and you will need to memorize some of these in all likelihood. But there's also some ways you can recognize when you're likely to have an exception and have a deeper understanding for what's happening in physics land. So let me jump over to our periodic table for a moment. And we'll start in with the same series that we have over in our slides. We started out with zinc, galenium, germanium, arsenic, selenium, bromine, and krypton. Now notice that what we're doing is we're adding in electrons. So if I start with zinc, unsurprisingly, the next electron that I add is going to be my 4p, then another and another, and then I'll finally fill up all the way up when I go to krypton. Now let's jump to the far side of the periodic table and take a look at what happens as we come across, though. So as we're filling things up, we end up having our 4s1, we end up having a 4s2. Things are behaving predictably so far. Scandium, we end up having it be plus 1 electron to the d electron. We're going to add a second electron, a third, a fourth, but wait a second. Why do we have a fifth electron suddenly show up in the d orbital? Well, take a look at the s orbital right here. We've only got one electron in there. Look at how close these are in energy. They're so close together in energy that it actually makes sense for the electron in the 4s, where it's pretty constrained and it's got a roommate. It's got a second electron in there. It makes sense for it to use the more room that you get from the 3d orbital. Remember how far out those extend. And all the different directions in space they can point. Now no electrons have to be paired. Now that only works because it only has to move one electron and they're really close in energy. And because of that, krypton is going to end up having a weirdness. Notice that when we had vanadium, we have two empty spaces in our d electrons and a totally full s orbital. And I'll show you again when we come to krypton, to chromium, you can see that our s electron got promoted to the 3d. Didn't take much energy, but it gave it a lot more stability by getting rid of the interference of having two electrons in the same orbital. Now let's keep going with our pattern. So I'm expecting that with one more electron and proton, manganese is going to fill up that 4s orbital, and sure enough it did. Things are well behaved again. Iron, same thing. Cobalt, nickel. Now wait a second here. I'll bet we're going to have something similar happen when we get to copper, because notice that copper, when we switch to there, we're going to have only one empty slot left in our d orbitals. Now yeah, that means I'm probably going to have a similar pattern emerge, right? And sure enough, look at that. This 4s electron got promoted up into this 3d orbital. Now why would that work? Remember, if we have to have that electron be paired either way, the 4s is small and has a lot of overlap between where both electrons are moving. Here we have a lot more space, and so that electron finally gets freed up a little bit. It's a little less constrained. It takes a small amount of energy to move from that 4s level up to that 3d level, but not very much. Oops, it didn't take much to do it at all. Because the small amount of energy that gives it a lot of extra stability, it happens. Now with zinc, things ended up filling up all the way just like we expected. Now, that means I'm probably expecting the same thing to happen for silver, and sure enough, look at that. Silver also promotes an electron, which means it ends up having a weird sort of filling as well. Now, I'll also point out palladium has that happen. Notice that palladium right now, we have our 4s totally filled and our 4d totally filled. But look at that. We stole from our 5s. We stole 2 electrons this time. Why? Again, because the 5s is very constrained. Don't forget, every one of the orbitals that happened before that exist. We've got a 1s orbital, a 2s orbital, 2p orbitals, 3s orbitals. All those things are all crammed in there by the nucleus. So all these electrons are really having a whole lot of space sharing. They are different orbitals, but they still have to share the same volume of space. That's really annoying. So in this case, there's actually enough interference there that it makes it worthwhile for silver to bump both of those electrons up to that 4d orbital and just totally vacate, for palladium to totally vacate the 5s orbital. So that's one of the reasons palladium's an exception. Let's come over to chromium again. We saw how chromium behaves, and molybdenum does the same thing. Now, I'll also point out though, when you get further down the periodic table, things get even more complicated because now you've got f orbitals around, and so things end up having a lot more complicated patterns. We aren't going to worry about the exceptions that are down in these 2 rows, or certainly nothing down in the F block. But I do want you to recognize the what and the why. Chromium, molybdenum, copper, silver, and palladium are all going to have exceptions to their filling rules. Now if we come back over to our handout, you can see really dramatically just how close in energy these are. We're just going to look at copper in this case. Look at how close copper and zinc are going to be for the energies that are shifting. We're taking an electron from the 4s and sticking it into the 3p. So let's see, a 4s, and sorry, a 3d. So a 4s to a 3d doesn't cost a ton of energy to make happen. Here we are. So that's how much energy it had to add in to gain a little bit of stability. And look, it's really not much energy when you look at the whole scale. And then when we got further down, when we were talking about further on the periodic table, when we had the palladium do the same sort of thing, for palladium, it was taking a 4d to a 5p. That's an even smaller energy gap. That's why it was able to cheat so much and get that extra stability as a result. Now, these are your 5 notable exceptions out of the transition metals. Pretty much everything else on the periodic table is going to behave the way that you expect them, at least as far as the filling rules go. Now that said, shouldn't we see something sort of similar when we can get a p orbital that's totally half filled? We'll see that there is an exception with that as well in terms of properties, but it isn't a strong enough exception to actually get it to cheat and move electrons around. It just gives it some neat properties. So the only 5 that you should know about are going to be copper, silver, chromium, molybdenum, and palladium. Now, you don't need to memorize those, but you should be able to identify the when and the why that they happen.